So good evening. My name is Karen Salkaitis, and I am the Dean of Arts and Sciences here at UAS. Welcome to Evening at Egan. Even though we are virtual tonight, we are hosted from Juneau. All of our campuses in Juneau, Ketchikan, and Sitka reside in Tlingit territory. Specifically, our Auk Lake campus in Juneau is located on the land of the Akwaan people. I ask you to join me in acknowledging the Akwaan and Greater Tlingit community, their elders, both past and present, as well as future generations. Thank you. It is my great pleasure to introduce Dr. Megan Buzby to you, presenting the real world from one mathematician's point of view. A bit about Dr. Buzby first. She attended undergraduate and graduate school in Colorado, receiving her PhD in mathematics from Colorado State University in 2009. While a graduate student, she participated in an interdisciplinary program funded by NSF for research and teaching in a cross-section of mathematics, ecology, and statistics. Dr. Buzby began at UAS in 2009 as an assistant professor of mathematics, and she teaches a wide range of courses from beginning algebra through upper division mathematics and statistics courses. At every level, Dr. Buzby challenges her students to explore math problems with real-world applications and to ask themselves about the meaning of these problems and their solutions. Also, whenever I'm introducing someone, I ask them for some sort of fun fact or maybe two fun facts. And when I asked Megan, she said that she was a sea kayak guide in Haines and Glacier Bay National Park for several summers since moving to Juneau. She also loves music and dance, which I was very interested in. And she's learned several styles of dance in the past 20 plus years, which Megan, we're going to have to talk about at some point. So I'm very excited to give you now Dr. Megan Buzby.
All right. Thanks very much, Karen. That was a lovely introduction. We will chat at some point. Thank you all for being here on a lovely Friday night after I'm sure a long week. And before I start my presentation, I just also want to say thank you to Karen Carey, our chancellor, for asking me to give this talk and for providing the sabbatical that allowed me to give it. So thanks very much. And thanks to all my colleagues that were holding down the fort at UAS while I took my year off and did some fun stuff and wrote a book that you guys get to hear about. So I'm going to share my screen with you here. And we're going to start, looks like somewhere in the middle, so I'll restart it here at the right spot. All right, can everybody see that title page? All right, great. One thing I should also say, I always run over in my classes. I'm going to say about 80% of the time. I'm going to try very hard to finish this at about 8 o'clock. So if you need to go before that, that is totally fine. But I will try to wrap up on time as close as I can. So I just wanted to say a few words about why the word real is in quotes here. One of the things that I like to think about a lot is just who cares about math? Why do we need to know? Why do I care? Why do I want to learn more about it? And I always found it funny when I first started teaching math, and I found myself using that expression, here's the real world applications. This is why you need to care about math. And it struck me as funny because almost all the time you give a real world problem and it's like some very small, sort of curt description, and it's even, kind of more straightforward than the actual real world. And so I think what I want to show you a little bit is the difference between what I see as the actual real world and then the mathematical real world that we use just to simplify situations into something that you can analyze with some mathematical tools. All right, so what I'm going to talk about today is a few things. Open access is a movement that's been happening for a while, and in particular, it's been really helpful for making research and education more accessible, less expensive. And so I'll tell you a little bit more about that. Sabbatical. So one of the things that I think sometimes people just wonder, like, what the heck is that? And it sounds pretty great, but I don't know what it is. So I hope to answer that question. And of course, I'm going to show you my book. I'll give you a little bit of a slight tour through it, and then we will talk about some honeybees for something fun in an application. All right, so at UAS, we have been talking about open access for quite a number of years, probably not quite as long as it's been a movement around the world. There are two faculty members that I remember specifically, Jonas Lamb and Jennifer Ward, were really great at advocating for open access and just kind of giving it a name when I was at a point where I sort of was wondering what are some alternatives to some expensive textbooks. The other place where open access is helpful is in research. And so a lot of attention has been given to providing information to people, especially when it's been publicly funded by your tax dollars. You shouldn't have to also then pay another fee to a journal publisher in order to get access to that information. So this freedom of information has been going around for a while, and at UAS, that is one place you can find that is at ScholarWorks at UA, or scholarworks.alaska.ua. And you can find research for all of the faculty at all three universities in the UA system. The other thing that open access is really helpful for is just in particular educational materials. So textbooks, lab manuals, any sort of additional reading materials that you might have your students read. It turns out those can be pretty expensive, and the costs are just rising and rising very fast. The other part about open access that I think is kind of interesting and maybe not as well known is that open access open access documents are often published under a Creative Commons publishing license. And that actually allows anybody to reuse, redistribute, and edit the work that you provide. So it's a little bit of a scary thing to like put your information out there and know that somebody is going to change it, they're going to use it. But that's an element of kind of exciting to see what people are going to do with ideas that kind of come around from different points of view and how they can adapt it and use it in different ways. One of the ways that you can give credit to that is just in the way that you allow, the way that you define the Creative Commons license. And so the license that I and my co-author chose were that anybody that wanted to reuse the work had to attribute where the original work came from, and they have to say if they changed it. And then it's also a non-commercial license. So I'm not making money off of my book, and it gets to be provided for free. All right, so again, kind of the big deals at UAS is students just spend a lot of money. I'm sure you know or have fellow students that are friends or sisters or sons and daughters that are going to school and spending a lot of money. Books is one of the fees that they end up having to budget for, and at UAS, it's about $700. And that's, I think there's plenty of students that spend more and there's some that spend less. And I think we're trying hard to reduce that number. Across the country, about 60% or more of undergraduate students don't even purchase the textbook because it's too expensive, or they're trying to weigh their priorities. Do they get a meal plan or do they get a textbook? And sometimes they try to be creative about how they access the information that they need for the class, which is a little scary when you're the one at the front of the room and you're expecting that, oh yeah, they've read their book, or they could at least read their book later when they're trying to work on their homework. And it turns out that that's not always the case. And so I noticed this with my own students. I saw that they were having trouble with homework, and I would ask them, I would periodically survey them and say, all right, how many people still need their textbook? And still, even 1 or 2 weeks into the class, some students wouldn't have their book. And I would tell them different places that they could get the textbook. but coordinating with a group to study for 1 hour when you guys have a common time block, it's just not conducive to studying. So I noticed it when I was teaching elementary algebra. I had a book that was $200. It's a semester-long course. The students are going to get a different algebra book the next semester when they take intermediate algebra. It's not like a shrine that they need to keep forever. $300 for a differential equations book. And I was able to find an open access book along with Andrzej Petrowski is another math professor at UAS, and we use the same open access book that's actually really good quality. It's been around for a while by William Trench. So I've been watching, seeing my students, realizing I have, play a big role in what textbooks my students have to pay for, what's required for the class. And so that really weighed in a lot into my choice to get involved in that. And then just with the math program at UAS, anytime we're talking about textbooks, we're also always talking about cost, and does it justify the cost to have this expensive textbook, or is this alternative comparable? All right, so maybe you can see this. I feel like I have a lot of Zoom pictures that kind of come up, but so this is some good stuff that's happening at UAS. This is information that Jonas Lamb pulled together. And this is for the costs. Even just on the bottom right, you can see in just the spring of 2020 to spring 2021, students saved almost $90,000 by the textbook alternatives that their professors chose for their classes. And so that's a big deal. It was an especially big deal the last couple of years. So I like that we're making some good progress in that direction. All right, so sabbatical, what is it and how do I get one? So it turns out you may need to become a professor. You may need to become tenured, and then after you've been serving at your university for 7 or more years, you can apply to get a sabbatical. I always remembered thinking that the word tenured meant 10 years. You got to do it for 10 years. And that's actually what ended up happening. I've been at UAS since 2009 and took my first sabbatical last year. So it's 1 semester or 1 year. And the idea is that you take a break from your normal teaching, your service, research duties that you have as part of your workload for your job. And so you get a break from that and you apply to study something different, go back to school. If you have a big research project or a book of poems that you want to write, you just have to choose something that benefits you in your professional position and supports the university. The other thing that is a consideration is you have a reduced salaries. You have to decide if that sort of works for you, and it helps the university out so they can allot some of that money to pay for an adjunct professor to cover your classes while you're gone. Also, the time off allows you to travel. You can collaborate with colleagues maybe you've known over the years, but you don't have a way to be in person with them or to collaborate the time to talk with them and meet with them. You're not tied to one location, so that's really helpful. And also just generally that time for larger projects, there's so many things that even if you had a half an hour every day to devote to research or writing, it just can't get done. You got to be in a mindset to be able to do it. And I'm sure lots of you have seen that in art projects or work projects or home improvement projects. Sometimes you just need a bulk chunk of time. So that's really great. And it's definitely just nice to have a change of pace, rejuvenate, and remind yourself why you like your job. And it's a really good fit. And yeah, allows you to come back, be happier, and make a better impact for your students and at the university. So for me, I made a plan to write a textbook with my friend and colleague, Dr. Sheldon Lee. He's at Viterbo University that's in La Crosse, Wisconsin. And so I plan to go over there in the fall of 2020 and then collaborate with him distance in the spring, and I ended up working in my office in Juneau in the spring, which actually worked out kind of great for lots of reasons. And then the idea was that I was going to publish this book in an open access repository, and so that I could use it for my classes. Dr. Lee could use it for his classes, and then we'd be able to put together all of our combined materials. Of course, I also wanted to travel, and I suppose I did a little of that, but I'm sure I didn't get to travel to Europe last year. So again, so here's a little bit of my motivation for why I chose this particular project. I and Dr. Lee both teach this modeling class. We went to a graduate school together. We both studied some interdisciplinary work, and I focused a little more on ecology and biology problems. He was looking for engineering, and there are just lots and lots of resources that that you pull together. The textbook options that are available, even if they're expensive, don't have your particular point of view all the time, and so you kind of I have like 5 different resources that I might use for my students, and that makes it a little hard for them to follow as they're going throughout the semester. So, so my approach was a little bit different than Sheldon. So I felt like we could collaborate pretty well, and also it was kind of at this time when I was getting excited about open access materials, and thought that that would work well for a publication for me and allow me to edit it and use it sort of quickly. And I also really wanted a break after that. I'd been serving as a faculty senate president in that capacity for 3 years. So that's a long job. And thanks to Andrea Deweese, who's doing it right now. All right, so so what actually happens? You make your plan. How does that actually work out? So it is a lot of what you think it might be. It's a lot of hours sitting at a desk and writing and editing what you've written and researching. I did a bunch of math problems to make sure they all worked out right. I coded in MATLAB a lot. That's the software program that we use with our students, and helps to illustrate some of the results that we have in a graphical form. And I did a lot of formatting in this program called LaTeX that converts text into nice, pretty mathematical writing. So you'll see that a little bit when I show you the book, and creating diagrams. So I did all of that, and I also had other things happen. So COVID-19 happened. That was interesting. I quarantined in my friend's house instead of my place in Juneau. So that was actually worked out really nice. I got to be outside. I had fall for what seemed like 2 straight months. It was beautiful, and got to explore new trails, running and hiking and biking. I bought a car so I could drive around and visit some people that I knew I wouldn't get back to for a while. And spent the winter up in Fairbanks. I have family up there. And like I said, I spent the spring down here in Juneau, and which was nice. My other math colleagues were in their offices, hiding out, teaching their online classes. And I also got to ski a bunch. So all good things. I did finish the book. I'm sure I'm going to make another edition, but I finished it at the end of May, and then started teaching again this August. So that took about a year. All right, here's some fun pictures for you. Just different places that I visited and I got to see that weren't Juneau. Got out of town, did some hiking, like I said. One of my favorite pictures is there in the middle, and it reminds me of the Big Lebowski and the dude. And I think about the only thing that I felt like I had in common with him, but it was sort of striking, is I just felt it was super luxurious to be able to sleep in or take a half an hour and drink my tea in the morning and not have to rush off to class. So that was pretty great. All right, so I'm going to show you my book. It's a PDF that you can access through ScholarWorks. There's the address for it. And there's my friend Sheldon. It's a great name for a nice, intelligent human. And this will take just a minute here. I think I'm going to stop sharing and share the PDF with you. All right, hopefully you can see this PDF. I don't see any head nods or any loud noises, so I'll assume that you can. Okay, so here's my book, and probably over here on the left, you can see some menu items. If you scroll down in the book, you can see our copyright license, and there's that Creative Commons license that allows you to reuse it, edit it, do what you like if you attribute it. And then you can see the table of contents here, or like I said, over here in the menu on the left side. LaTeX is kind of a two-step program for typing. So you kind of like HTML code, you have the code that you write, and then you compile it, and it produces this PDF. So I'm able to link things that are highlighted here in these red boxes, and you can go back and forth in the document, which makes it a little easier to navigate. So let's just take a look. So if I wanted to figure out what the heck is this programming in MATLAB, so there's a little bit about why it's important, and I'll let you read that. I will just say programming just in any language is really helpful, particularly if you're going to go into math or science or engineering. It's used in lots of, so many other ways, the arts and visual programs and all sorts of things. But whatever you're programming, I don't think it really matters too much what language is in. It just helps you get started so that you can learn other languages as you need to. I think I learned my first computer program was on a TI-83 calculator from my high school math teacher, Mr. Dan Hackett. All right, so here's a little snippet of what the MATLAB directory looks like. And you, in the center here, this is the command window. So this is where you might type your equation, or type a command to run your code, or x plus 7, what does that equal? And then you have a list of files over here on the left, so things that you've saved so that you can repeat a bunch of commands without having to type them individually line by line in the command window. It's often important when you're coding to figure out what size your variables are, to make sure that the math of multiplying matrices together is going to work out, or what you're plotting is actually what you think you're plotting. And so that's another sort of tool you can use over here. So just some different aspects, and I think I'll let you explore that if you're interested. And just a little bit more, and then we'll go back to our presentation. So we've got some MATLAB basics, little reminder when you're multiplying with matrices. And you probably remember a matrix is just a structure for inputting usually numbers, but expressions and other things can be used. So it's got an m rows and then n columns here is how you would define it. And if we scroll a little further, we've got a little summary of some of the other MATLAB commands, what they do, and all in one place. And then if you click on the activity here to get a little practice, you can click on that and get yourself started in doing a little MATLAB. Decide you're done with that, you can go back. So you're going to hit the back arrow, but you hold down the Alt key. I just find this an incredibly useful tool, and I'm sure you all forget it, but just so you heard it once, hold the Alt key down and go backwards, and it can take you back where you were. You can keep reading and doing what you want to do. All right. Okay, so I think that's all I'm going to say about the book right now. Again, that's at scholarworks.alaska.edu, and you can check that out. Go back to our presentation here. All right, so what the heck is mathematical modeling? Mathematical modeling is a process of using mathematics to describe and analyze real-world phenomena. All right, so like I mentioned, in school, so I have a friend who has an elementary school age son, and this was his real world problem, trying to figure out how many cartons of milk Mervyn had. And when you go a little further, maybe you just took a college algebra exam and you had to figure out the optimal dimensions of a rectangular field if you only have a certain amount of fencing. So they feel like that's a little bit more real world. If you're a gardener, you're a farmer, you've got some animals, you probably want to try to conserve your money that you spend on fencing, but you want the most area for your buck. So that's a helpful problem to be able to solve. Like I said, though, and like you all know, the actual real world is less prescribed. There's more questions. You often don't even know what the question is. So you have to make that decision. What's the question that you're going to study? You have to be specific enough that you can put it in mathematical terms. The other thing that's interesting is, how do you know that your results are accurate? How do you know that they're good and what you were looking for? So here's just a little diagram of the modeling process. This is another Creative Commons document that is from Vicky Yang. So starting in the real world, it's not just a one-directional process. We're going to start with the question, what are you interested in? Define it in an actual math problem, and then you're here living in this world that I and my math colleagues like a lot, and you get to use all your mathematical tools, solve the equation, solve the problem, and then just go back and see, how does that apply to the real world? Did it work? Does your data support that model output, or do you need to go back and try it again? All right, so it's kind of a process that I try to convince my students, right, that it's okay to get an answer that looks funny. Just go back and see if there's some other way you can change the problem. Okay, so today we are going to look at honeybees and their foraging behavior. And I'll just give you kind of some background if you don't know much about bees. I know a tiny little bit about bees. My sister Wendy, who is maybe still on the call, likes bees a lot. And my grandpa had bees for a long time, so they're kind of fun. They've also been in the news quite a lot lately. So they flap their wings a bunch. They require a lot of energy, and where they get their energy from is the nectar. So they go fly out, get the nectar from the flowers, they bring it back to the hive, and there's receiver bees. So they suck up all of the nectar, they regurgitate it back out and give it to these younger bees who do more processing and turn it into honey and use it or store it. A little information about nectar. It's also risky for a bee to travel outside the hive. So it requires energy. They want to be efficient about that process. And so one of the questions we might ask is, well, how can we understand their efficiency a little bit better? It turns out they also stop foraging for a couple of different reasons. If the nectar decreases in quality, or if the hive is full and they don't need any more. All right. And it turns out there's other things that might stop a bee from foraging. And there's a little bit of communication that is sort of fun. You've maybe heard about the waggle dance. A bee comes back to the hive and does a little dance that says something to the bees and tells the other bees a little bit about the location. Where should they go back? Was the quality of nectar good there? And they also collect pollen and make propolis in their hives for structure and for sometimes isolating out things in the hive that they don't want to get mixed up with the honey. All right, so I'm going to switch the screen again and give you a little video to watch. Okay. You may need to adjust your volume up or down. There's a fun accent here that sometimes might be soft.
They keep licking up nectar till they have filled their special honey. Check out this bee's tongue. Look at it licking up the nectar from this basil flower. Each foraging bee will visit 50 to 200 flowers on any one trip, collecting both nectar and pollen. They keep licking up nectar till they have filled their special honey collecting stomach. A bee can carry its own body weight in nectar and pollen. It's amazing they can fly home at all, really. On her trip back to the hive, she uses enzymes and proteins to break down the complex sugars from the flower nectar to simpler ones less prone to crystallization. This process is called inversion. If she gets a little hungry on the way, she can feed herself by tapping off a bit of the nectar from her honey stomach to her shack. She then arrives back at the hive and regurgitates her sugary offering to another younger bee to process it further. In the bee's stomach, a lot of the water gets absorbed. This reduces the watery nectar to honey. Then it's deposited into a honeycomb cell. The final bit of condensing is done using bee air conditioning. This is where the bees fan their wings, creating currents of air throughout the hive, reducing the honey down to an optimal water content. When it's ready, the bees put a wax cap on the cell to store the honey for later. Isn't honey such an extraordinary thing? When you think about it, the nectar of millions of flowers collected from 7,000 acres or more around the hive, all condensed down by the bees into liquid gold, and often full of amazing medicinal properties. No wonder they say beekeepers live longer.
All right, kind of a nice fun video there. So what we want to do then is to try to take all the interesting questions that we might come up with about those honeybees and try to convert our question into a math statement. So here's one question that Sheldon and I proposed in our book, and we'll talk about here. So determine the rate at which a bee collects nectar and the optimal time that a bee spends at each flower. Okay. Here are a few assumptions that we need to make if this is going to be transparent, right? So I can answer this question without telling you what the assumptions are, but you're going to question the result, and you should, right? When does this rate apply? If I tell you a time, what else is going on in that situation? So the other thing that's good about listing your assumptions is that when you want to add a little complication to your model, if you think you want to incorporate some other component, you can go back and figure out what assumptions did you have in the beginning and what needs to be changed. So we're going to assume in this type of model that every bee collecting nectar behaves in the same way, and every flower has the same amount of nectar that's available. And usually that's a pretty good assumption if you have the same type of flower in a field. So we've got all of our fireweed that's in a great big field, or lupin that's in a great big field. And so that seems a pretty reasonable assumption. The other thing that we're going to assume is that there's plenty of flowers. The bee doesn't have any other competition. There's no other butterflies that it's having to navigate around, and that the flowers are evenly distributed. So that's kind of interesting. We're assuming that there aren't little clumps, that every flower, if a bee was to fly between the flowers, it would take the same amount of time to fly between each one. Other factors that might affect the bees' flight time or their ability to collect the nectar, we're going to assume that the weather's at least consistent, so that it's not changing within the time span that we're looking at. There's also no predation. There's no birds that are flying around looking to eat the bees. Another thing that we're going to assume is that the longer a bee spends at a flower, the slower the nectar comes out. So if we don't have that assumption, you could assume that a bee might just sit at one flower, collect all the nectar, and then leave. But it turns out when there's less nectar, it doesn't come out quite as fast. So the bee has to decide, do they stay at the flower and get it all, or do they move on to the next one? All right, so in particular, what we're looking for is an equation that we can write down that gives the rate that a bee collects nectar. And I'm going to ask this question for the rate and not the total amount of nectar. It turns out it's a small change that we can make to get the total amount, but it changes quite a bit between different types of flowers. All right, so in the modeling process, before we write this equation down, we want to define the pieces that we have. So we're going to let R of T be the rate that a bee collects nectar T seconds after it arrives. So when T is 0, there should be no nectar coming into in for the bee. P of T is the proportion of nectar that's consumed. I'll talk a little bit more about that. And N is going to be the number of flowers that the bee visits, and tau is going to be the flight time between flowers. I thought about not including this tau or changing the variable so that it doesn't look funny, but one of the things I like about math is we use a lot of Greek letters, and so tau is spelled T-A-U, and it's often used for a time variable. All right, so here's one way to express the rate of nectar consumption. Generally, it's just a ratio, right? The ratio of the total nectar that the bee consumes divided by the total time that he spends, that he or she or they spends at the flying around getting all that nectar. So one way that we could compute that is to look at the proportion of nectar consumed per flower and just multiply by the number of flowers we have. And divide that by the time that the bee spends on each flower and the number of flowers. And so over here, we can see that that N factor is going to cancel, which simplifies our model just a little bit. The other reason that we're doing that is because the proportion is sometimes easier to get information for. All right, so here's that equation again with the simplified expression there on the right side. Okay, so what do we mean by the total nectar consumed? Another way that you can think about that, if a bee leaves before it collects all the nectar from a flower, you could think, for example, that if a bee consumes 80% of the available nectar from a flower and then it visits a total of 10 flowers, you multiply 80% times 10, you get 8. So that's basically saying that you have the equivalent of 100% of the available nectar from 8 flowers. Right? So that's one way you can think about that. What do we mean by the proportion consumed? So again, in that equation, the N cancels out. So the units that we're looking at are the proportion or the percentage of nectar consumed for each flower per unit time. So for example, 34% of the nectar may be consumed per second if I'm dealing in units of seconds for time. Okay, so one of the things that I like about modeling and that I try to help students as they're taking classes that are kind of come up before they might take modeling, so college algebra or trigonometry or calculus, is just understanding what a function is, different properties about the function. So I'm going to talk about that. The proportion function that we're going to use is t divided by t plus 0.5. The units on the top and the bottom are seconds. And it's certainly worth asking why this function. And I'll just say the short version is that it's because the properties of this function match the assumptions that we're going to use in our model. And so I'm just going to go through some of those. All right, P of T is unitless, so proportions don't have any units, so they're just a percentage or a ratio. And if I have time in seconds in the top and time in seconds in the bottom, that works out. This 0.5 is a parameter that we could change if it doesn't match our data. We could change that value, but it has to be in units of seconds if I'm going to add it to something that's also in seconds. All right, so a couple of those assumptions. When a bee initially arrives, when time is 0, the proportion of nectar collected is also 0. So if I have a function and I plug in 0 for t, then yes, that turns out to be 0. So that's good. And then as the proportion is P of T increases, the longer the bee spends at each flower, okay? And so, of course, the amount of nectar that the bee collects increases, and so does the proportion. And so one way that we measure that is by looking at the change in P of T is positive as T increases. So if I look at two values of time where T1 is the first time and T2 is some later time, then the proportion at the later time has to be larger than the proportion at the initial time. And so that just says the difference there is positive, and that changes a mathematical way that we say we have an increasing function. All right, but we can also do it a little cleaner, a little nicer with some calculus. So P of t, if that derivative of P of t is positive, that also says the function is increasing. So I'm going to go through just a little bit, I think the next couple of pages about calculus. So if you remember it from high school or that time you took it in college, or you took it a few years ago and you do higher level math now, here's a good little reminder for you. So the derivative, you just want to think about the derivative as the change. In this case, it's the change in P as time changes, right? So we could take the derivative using our quotient rule, and low d high less high d low over denominator squared will go. If you're in high school, you probably know what that is. And it's a positive number. We've got 0.5 in the numerator. The denominator is positive because anything squared is positive. So that's good. We also assumed that the rate at which P of t increases decreases with time. So that's a kind of a complicated sentence there. So P of t, the rate that we're collecting nectar, the rate the proportion increases, is still positive, but it's decreasing with time. So there's not as much nectar coming out. There's still nectar, but the change is getting less as time goes on. So the way we think about that is the change in the change, or the derivative of P prime, is negative. So it's decreasing. And we can see over here, this expression for the second derivative is -1 in the numerator, and this denominator is positive as long as t is positive, right? We just care about positive time and not going backwards in time. So that's a negative fraction. And if you remember that second derivative being negative tells you that your function is concave down, which you can think about as a bowl. If you took a bowl and turned it upside down, that shape of the bowl is concave down. And if you took the bowl and turned it right side up to hold your bowl of soup, that would be concave up. All right, another assumption that we can verify with this, that this function works, is if the bee spends as long as it wants, as long as it can at each flower, it would eventually collect all the nectar. And so what we mean by that is we can express it as a limit, or a limiting process, that as t goes off to infinity, super large, huge numbers, if we really need it to, this ratio approaches the value of 1. And that's a whole fun thing. You could take calculus to really get into the details of that. But just think about as t gets really large, it doesn't matter so much if you add 0.5 or you add 2.5. The ratio of a number and that really huge number plus just a little bit is still pretty dang close to 1. Right, oops, sorry. So there's the function for the proportion. Notice that it's increasing pretty quickly for short values of time. And then as time increases, the change in that proportion is getting a little smaller. And so we can see the assumptions that we wrote out in equation form, we can see in this graph. So the initial value of the proportion is 0. We can see the first derivative is positive, and that's just the slope of a tangent line. So if you drew a line touching the curve at just one point, it would have a positive slope. And again, that second derivative is negative, tells you have a concave down shaped graph. And if you try to put soup into that function, it would fall straight out. And the limit here of P of t, the limit of P of t as t gets large does approach 1. So the proportion, I should have mentioned earlier, is in this blue color, and this P equals 1 is just a horizontal asymptote, just to show you visually that we are approaching that value of P. All right, so we have our proportion, and what we really want is that equation for the rate. Okay, so the rate is the proportion of nectar consumed divided by the total time that a bee spends per flower. And so what we've got here is this time, little t plus tau. So the time t, little t, is how long the bee spends at each flower, and tau is the time it spends flying between each flower. And so we've got the sum of both of those to include in our time. If I take P of t divided by that expression t plus tau, I have my new function for the rate. Okay. All right, and then we've got, like I said before, the units of proportion or percentage of nectar consumed per unit time, and tau is that travel time between flowers. Here's the graph of that function. So it looks a little pretty different than our proportion function. It increases, so this is the rate of our function, the function of R of t for the rate is increasing. And then at some point you notice, right, that the graph stops increasing and the rate of consumption goes down. And so we're trying to find that optimal time t where the rate isn't going to get any bigger. And that's when the graph changes between an increasing function and a decreasing function. All right, so we'll label that value of t as t star. A side note, it does just depend on the value of tau. Tau is, again, a parameter that we're going to be able to change if we want to adjust to maybe some data that we have. So the variable that we're looking at is t. Okay, so we want to find that time, the optimal time. And so in calculus, that's when the first derivative is equal to 0. So here's kind of our sort of messy first derivative. And when we have a fraction equal to 0, you can solve that by just noticing that the only way that a fraction can be 0 is if that numerator is 0. And so we really just need to solve this this quadratic equation, and we get t is equal to the square root of 0.5 times whatever that tau value is. So believe it or not, that's the solution. That's what we wanted in all of our modeling process. So now we've determined that the optimal time a bee should spend at each flower collecting nectar is this value, square root of 0.5 times tau. All right, so just looking at that a little closer, here's 3 different graphs that we can get for the rate function if I use different values of tau up here in this legend on the top of that graph. So for tau equals 1, we notice that the rate function is the largest it's going to be for those 3 values. And we have a relatively short time that the bee is going to spend at each flower, so 0.71 seconds. If the time between flowers is 2 seconds, which is probably a long time for a bee to fly for 2 seconds without getting to a flower, then the optimal time that it spends at each collecting nectar is just 1 second. And then if it takes 3 seconds to travel between flowers, they are gonna spend 1.22 seconds at each flower to get the optimal rate of nectar collection. All right, so that's just another way to see it in a equation. And then I also gave you the values of the rate R of t star at those maximum points. And so 34% of the nectar is consumed per second if the time between travel time between flowers is 1 second. And then that rate decreases as tau increases. All right. So that's what we can deliver back to our beekeeping folks. As the travel time between flowers increases, the bee spends longer at each flower to maintain the efficiency, and the maximal rate of nectar collection goes down. So you might want to ask then, right, what are the changes in those foraging areas that might cause travel time between flowers to increase? Okay, so those are some outside questions that I probably don't need math to tell me what are ways that that change the distribution of flowers. I could make a mathematical model to see it, but I could also take some data. I could also work with a biologist who might be, or a botanist, and go out there who would be studying flowers. Right, climate change probably has an effect, maybe a change in the soil. Different animals foraging in those areas, right? So those are all things that are kind of a bigger picture that we can ask about this question. All right, I am doing pretty good on my time, so I get to show you a couple of different refinements that we might just think about with this model. So one of the assumptions that we made is that the amount of nectar in the flowers is the same for all of the flowers. What if the rate of nectar collection changes depending on the time of day? All right. So here's one option that I just added just to give you a flavor for how things might change. And so we put a lot of sort of stock into this proportion function. And I just went from one input variable to 2, and I'm teaching calculus 3 right now. So they would, I don't know if they would love this problem, but they have might find it interesting. So we've got our proportion, and then I'm multiplying it by this extra factor for the sine squared of pi over 12 times x. So that parameter in front of the x changes the period of that sine function. And so it allows us to look at the time of the day with a 24-hour clock. So the sine function starts to repeat every 24 hours with this extra parameter. All right, and so if that's the proportion function, then the rate is still the proportion divided by the total time. So you see it's exactly the same as the proportion, but we have this extra factor of t plus tau in the denominator. Here's a fun picture graph of that function. So if I input 2 different variables, I've got to account for that. And then the third variable gives us a third dimension when we're graphing it. So you can see the scale here on the bottom left. The time values go from the back, starting at 0, 1, 2, 3, 4, 5. And it looks a little funky here with the x values. The 0 for x equals 0 is underneath the 5 for time. So it does actually start at 0 and goes by 5s along the bottom right. And then the rate is the z-axis or the vertical axis there. And we can see it goes up a little bit above 0.3. And so we might ask the same question: what's the maximal time that a bee might spend at each flower in order to optimize or get the most rate of nectar collection? So in the function that I chose, that looks like there's 2 different points where that might happen. And the way that I solve for that maximum point is pretty similar to what we might do in our last function that uses single variable calculus. So with multivariable calculus, we find out that the maximum gives the same time value, but 2 different times of day are going to give us that maximal time for our nectar collection. So I put on a 24-hour clock. So at 6 a.m. is the first maximum, and then 6 p.m. would be the second maximum. And I think if it were me, I'd probably go back and see if that was actually accurate compared to some data. Just knowing what I know about the sun, I imagine that flowers start to close up pretty close to 6 p.m. But it does turn out that nectar is produced just before the sun comes out and opens them up. So it's maybe a reasonable idea that the best nectar collection happens in the morning. All right, one more model choice that maybe be interesting for you. So can we account for changes in the weather? And so I added this little bit that just to show you a different type of model. So again, the structure of the model changes the mathematical tools that we use to solve it. It also changes what we know about the how we might talk about the solution. So here's what's called a stochastic addition. And so I'm going to let y be a random variable. So that just means a number that takes on different values by random chance. And you might think about a die being rolled that has 3 different numbers. I'll give it 1, 2, and 3. And so if you roll a 1 on the dice, then the proportion of collection, we're going to say, decreases by 90%. And if you roll a 2, nothing's going to happen. It's going to be the same original proportion that we looked at. And then if you roll a 3, then we're going to say that the proportion of collection increases. Maybe the sun came out a bunch for that random point. One thing that I just want to throw out there that's a little bit just contrived here is I'm going to assume that the weather changes every second. So we're going to change this random variable every second. And that's probably a little too much, maybe every 15 minutes, maybe every half hour, maybe once a day, there's a big storm. So there's different ways that we could define this random variable. But that's how I chose, just to give you a little bit of an example. All right, so what does that mean? So what that means is that our proportion then is going to change every time this random variable changes. And so we're going to think about every second, we've got to reassess what's that proportion. So P sub n, now I'm going to label that proportion as what's called a discrete value. So it changes in discontinuous points of time. So every second we'll get a new value, and P sub n, so on the nth second, we're going to get the same proportion right at our time. But we're multiplying. I added this different period for this function, and I changed it to a single variable with the same t being used here. But then I'm going to multiply by this extra factor over here. And so y was our random variable. I subtracted 2 so that I could just plug in the value. So for example, if y is equal to 2 and I roll that dice, 2 minus 2 is 0. So that term goes away. So all that happens is I end up just with this, the first 2 factors with the proportion and the sign function. If y is 1, for example, then this factor is -1, and I'm going to take 1 minus 0.1, which gives me my 0.9 percentage of what it ought to be otherwise. All right. Okay, so that gives you a little bit of a flavor for different ways, different models that you can use to understand something like nectar collection or rates or proportions of something changing in your environment. So of course, the last step is, again, to validate the model, look at some data and see how well it matches. I'm going to leave that part out just in the interest of time. And just go back to some things that we talked about, actually that I talked about while you guys listened politely. So just again, I am grateful to have had a sabbatical last year at all, but in particular last year was really helpful for me, and grateful for the folks that that stuck it out and made it through last year and learned a lot. Open access is a thing that more and more people are becoming involved in. Just like anything, when you start out something sort of new, it takes a while for the quality to build up into something that's useful. And so making that call about the cost versus the product is important, but as more people get involved, I think the quality is going up pretty quickly. So the mathematical modeling process is, again, kind of the big idea that I try to bring across in my math class at UAS. It has a Calculus 1 prerequisite that you can sign up for in the spring. So I hope that you could see a little bit about how useful of a tool math can be. Also, just that math is neat and really interesting, even if it's not used in real world problems. And just different ways to build a model. Again, those assumptions are super important. They change a lot. What you put in is what you get out. So pay attention to those. And then, like I said, with the bee models, if you pull in information from somebody that's a beekeeper, if you pull in information from somebody that's been around gardens a lot, there's a lot of information you could find out that can add to your model, that can add to your understanding of what the model shows you. All right, and there's our honeybees. They, according to the assumptions that I made, the model shows that the foraging rates for honeybees decrease as the travel time between flowers increases, which seems to match pretty well what you would expect. So that's what I have for you. Here's another example of a Creative Commons license as a photograph of a bumblebee on a lily. All right, thank you guys very much. I'm going to stop sharing so we can see each other. I do have some references here if you want to look at them.
Well, we can open it up to any questions if anybody wants to ask Megan something or tell her something. I would just encourage you to unmute and go ahead and ask.
Yeah, Megan, this was fascinating.
Great.
I've always wondered what modeling did, and having you talk about the honeybees was great.
Sweet.
Could you
Glad to
talk
hear
a
it.
bit about how you got into math? I know we've talked about that before,
Sure.
but
Yeah, how did I get started?
back to you.
Yeah, I think, I feel like I hear this story with anybody that likes math. They liked it because they had a good teacher and connected with a teacher. The teacher challenged them and they just were inspired a little bit. So I had a couple of female teachers when I was in junior high. I remember the first time that I saw a proof in algebra 2. So I saw the proof completing the square to get the quadratic formula. And I just, you walk through all these steps and then poof, at the end, there's the formula, like, oh my gosh, I've seen that before. So I thought that was pretty neat. And when I first started, I wanted to be a junior high math teacher. I sort of felt like junior high was a point where lots of kids kind of switched between, oh, I really love math, and then, oh my gosh, math is so hard. And I wanted to make a difference with those kids. And then I got through a little bit of school and decided, maybe I might be better suited to college teaching. So that's where I went with that. Oh, you're on mute, Karen.
Yeah, I know. We've only so you got into honeybees because of your father?
Oh, no, I got into math. My grandfather.
Okay.
I actually don't do anything with bees. I think they're great and neat and amazing. And my sister really gets into them. But my grandpa had bees right on the Chena River in Fairbanks. And so my mom took it up for a little bit. My cousin does it now. And my sister has honeybees, and that's kind of interesting. A lot of people are getting into them. They've been in the news, a lot, just that their populations are declining. So yeah, seems like there's been a
Your modeling
resurgence.
helped the honeybees survive.
Yeah, I think if you ask the right questions, if you, I think one of the questions there about if you recognize that it's detrimental to a bee to have to spend energy flying between flowers. I think one assumption would be if you plant the flowers, they will come, and it's one option.
Great, thank you.
Uh-huh.
I think Laura has a question.
Yes, Laura.
Thank you, Megan. There's actually a couple of us here watching Megan, and the question is actually Andrea's.
Oh,
Okay. I have two questions. So I liked how you complicated the problem as you went on by like adding some of the variables. So I was wondering what's kind of an example of a very complicated mathematical model? And then the other question I have is like, what's the weirdest mathematical modeling?
The weirdest mathematical model or the weirdest mathematical modeling scenario?
Scenario.
Okay. So I think the most complicated math model that I've heard about is weather models. They have, I think I was doing an internship with some folks that work in there's a national lab in Boulder, Colorado, and they were working on a weather model that had over 700 variables in it, and keeping track of them all. And a lot of times how weather models work is it's a probability model, and they have all of these different variables, and they give them all probabilities that they're going to happen. And so there are different results depending on how the dice get rolled. And so then what they can end up choosing is they choose the outcome that looks like it has the highest probability. So sometimes what happens when those rare events like a tornado come across, they might have seen it, in one of the 100 different simulations, but they said, the likelihood of that is probably pretty small. So they didn't report it. So whether folks have to make those decisions all the time. Let's see, the weirdest one. I don't know. That's a good question. I don't know. I think it's a little bit maybe unfair anytime we try to put math on things that aren't mathematical and strap a number onto something because it makes us feel better. So I don't know. I'm sure you could find some of those, but I don't know. Any of the other math folks, feel free to chime in if you think there's a weird model I presented that you're like, oh, that one's no good. Any other questions? Oh, thanks, Sanjay.
Okay. Well, this has been recorded, so if you have any friends that you want to see this, it will be posted sometime within the next week. You just go to the same page where you registered, and the button that says register here will change to watch video, and it'll take you to the YouTube channel. So I want to thank Megan for being a part of our program this year. So
yeah, thanks very much, Kenny. Thanks for hosting and putting all these together. I think it's a great thing that we do.
yeah, you guys are
Thanks
awesome.
everybody for coming.
Thank you, Megan.
Thanks.
Megan, thanks so much.
You're welcome.